Okay, we're going to be having a look at a rotational equilibrium problem. Also known as a torque problem. Okay, we're going to be looking at a ladder leaning against a wall. That's the wall, there's a floor, here's the ladder. Okay, we're going to make this interesting by placing someone on the ladder. Of course, they don't know how to stand on a ladder. And we're going to be given some information here. We'll say the mass of the person on the ladder is 50 kilograms. They are 3/4 of the way up. We have a 5-meter ladder. We have a mass of the ladder of 15 kilograms. And it's a uniform, meaning the mass is evenly distributed throughout that object. We are going to give an angle the ladder forms with the floor of 65 degrees. And this is our floor, I'll just label it. And the rollers on this ladder are going to provide a coefficient of friction equal to 0. In other words, no friction is going to be between the ladder and the wall. Alright, so we established an algorithm in class. That algorithm read as follows. Remember that an algorithm is a set of steps that we follow in order to find ourselves standing in front of answers. Before I actually head any further than that, I just want to state the question. Okay, the question that we're going to be looking for is find mu of the floor, I should say between the floor and the ladder, so as to prevent slippage. Okay, so that's your question. So back to the algorithm. A torque problem is going to involve eventually showing that the conditions of equilibrium, which is the sum of the torques counterclockwise about a chosen pivot point, must equal the sum of the torques clockwise about that same pivot point, and the sum of the forces in the x has to equal 0, and the sum of the forces in the y has to equal 0. Now, in order to make use of these and make sure we don't make any mistakes, this is what an algorithm is all about. So we want to do the things that are necessary for making these equations be true when we're solving them. Okay, the things that are necessary, we have to mention all of the forces involved. We have to identify the rigid body that torque is acting upon, which in this case is the ladder, and identify angles and so on. So this is what this algorithm makes use of. So in short form, I will put it like this. We want to identify our rigid body. I'll put that as rigid body question mark. 2, I want to label all external forces. And that is including the consideration of Fx, Fy at each point of contact for the rigid body. So I'll just state 3 is the conditions of equilibrium now. Sum of the torques clockwise has to equal the counterclockwise torque sum, and that the sum of the forces in the x equals 0, sum of the forces in the y equals 0. So these are conditions that are necessary for rotational equilibrium, and since they are necessary, we can use them to find unknowns, because we know if it's in equilibrium, this is true, what must be the value of these forces, where must they be, that type of thing, what angle must they be on in order to create the equilibrium that we see in front of us. So now let's just take this slow walk through our algorithm. We have the rigid body, which is the ladder, external forces. So the external forces acting on the ladder, the earth on the ladder, I'll call this FG1. Oh, actually I'll call it FG2 to correspond with the mass 2 here. And we have this person standing on the earth trying to pull this guy through the ladder. So the ladder has to provide an equal and opposite force to maintain its shape. That is our FG1. Those are all the forces acting on the ladder due to gravity, or gravitational forces. We have here now a force that the wall is exerting on the ladder. I'll call that FW. There is no force parallel to the surface, no force of friction, because mu is equal to 0 there. Down to this point of contact, remember we're trying to consider both Fx and Fy. That's what we did here. We consider our Fx and our Fy, and we're going to consider that here. I would believe that the force of friction would be acting like this to keep it from slipping, so I'm going to actually label it that way, force of friction to the right, and a normal force acting upwards, Fn. Okay, so I've considered both x and y at each point of contact with the rigid body and all external forces. And now we're going to head into torques. Now, our understanding of torques, we have by definition torque equals the force applied to the rigid body times the sine of the angle that the force makes with that rigid body. That is the percentage of the force. This is its percentage. So the percentage of the force acting perpendicular to the body times the distance from the pivot point. I'll call that dP. So that'll be the consideration for any force acting. So in this case, when I go to solve this problem, I will be choosing this as my pivot point. We can choose any point as a pivot point. There's nothing that suggests otherwise. We choose a pivot point so as to eliminate as many variables as possible. And in this case, we don't know the force of friction. If we choose this, that eliminates this in the torque problem, because the distance from the force of friction to the pivot is 0. The force of friction acts at the point of pivot. The angle theta for these guys here, we will figure that out as we go along. You realize it's going to be tied in with that 65, and then we can make use of that. Okay, I like to motivate you to run into your problems rather than pile up answers to problems or unknowns before you start solving. There's no way to avoid what you need to know. So now we get into solving this problem now. So now I'm going to write down the sum of the torques, and I will form that full equation. So the sum of the torques counterclockwise about a pivot equals the sum of the torques clockwise about that pivot. Counterclockwise are forces that cause the object to rotate, or have a tendency to rotate in the counterclockwise direction. So I am looking at the ladder here, just to make sure that we have this clearly explained. I am going to make this my ladder. And I can talk about each one of these forces. So the force here from the wall, I'm holding now the pivot of the ladder still. If I apply that force, it'll cause a rotation about that pivot in the counterclockwise direction. So the force from the wall is going to contribute to the counterclockwise torque. Similarly, if I pull on this FG, it will pull the ladder this way about the pivot. Notice I'm leaving the pivot in its place, applying the force causing that rotation in the clockwise. So both FG2 and FG1 will both be contributing to the clockwise torque. So the counterclockwise torque will be due to the force of the wall, and the clockwise torques will be due to the force of gravity on the ladder plus the torque due to the force of gravity between the person on the ladder and the earth. Now we are ready to start making substitutions. Torque is force times distance, or I should say force contributing to the torque is at a right angle to the beam. So I will have to consider what is the angle that this force makes with that beam. What is the force that these are making with the beam? So I know that that's going to happen now. I'm going to go up and consider that on my drawing. So I know that if I extend this down into a right angle triangle, this angle up in here is going to have to be 25 degrees. I extend my force from the wall, and I see this is the angle that it ends up making. Maybe I want to refine my algorithm to read the acute angle that the force makes with the beam to make sure that I'm looking for the right angle. So I can see that that angle is equal to the 65, and now I'm ready to put in clear expressions for my torque. So I have torque due to the force on the wall is force wall times the sine of the angle it makes with the beam, 65. That'll give me the percentage of the full magnitude of Fw, which causes torque, times the distance up the beam. It is a 5-meter ladder, so that's 5. Maybe you want to put brackets around this to make sure that things end up going in your calculator the correct way. Fg2, the force, Fg2, times the sine of the angle it makes with the beam, 25 degrees, times the length or the distance from the pivot point. This happens to be, it's a uniform ladder, so it's halfway up that ladder's length, so that's 2.5. And plus Fg1 and its percentage acting perpendicular to the beam, sine 25 degrees, times its distance up the beam, which we have been informed it's 3/4 of 5. So I walk through thinking about each one of those torques individually. I'm not considering even what I'm looking to find at this point. I'm just allowing this to dictate what I know is true about the situation. And now I can consider what things I know and don't know and solve for my unknown. I know masses, so I know Fg for both of these. So the only thing I don't know is Fw. I will isolate that Fw right now in my mind. So I know I'm going to be dividing by 5 sine 65 both sides. I will substitute in my values for mass times gravity. That's 15 times 9.8 sine 25 degrees times 2.5. Fg1, 50 times 9.8 times the sine of 25 degrees times 3/4 of 5, 15 over 4. And I will divide that all by, since I'm multiplying both sides by 1 over 5 sine 65, divide by 5 sine 65. So there you have it. I punched it magically through my calculator in less than the amount of time it takes light to travel from here to the paper. And I have a force acting from the wall of 205.6 newtons. Stored that in memory bank A. And now I can look at my other two conditions of equilibrium, the sum of the forces in the X needing to equal 0, and some of the forces in the Y needing to equal 0. We are interested in the force of friction because it has that coefficient in that. So that's the equation I'm going to go after first. And we quickly realize that the force of friction must equal the force the wall is exerting. So that leads us to the solving of mu from this equation. Mu Fn, so 205.6 divided by Fn equals mu. And now I consider, I don't know what Fn is right now. I'm just going to have to use the sum of the forces in the Y to find that. So sum of the forces in the Y, I quickly determine that Fn is equal to Fg1 plus Fg2, which is 637 newtons. So mu equals 205.6 divided by 637, and that gives us an answer 0.32. That was fun.